So now, just to recap what we have discussed about rate limiter implemented in a single server environment. So first, a client sends a request to the server. So the request is first being forwarded to a rate limiter middleware. So we have discussed about the rules also. They are stored in the disk in form of config files. So these rules are pulled down by workers and stored in cache frequently. So workers does this in a certain frequency and pull the rules from this, pull the config files or the rules from the disk and put them into the cache. So once our request is forwarded to this rate limiter middleware, it interacts with this cache to get the rules. It also interacts with Redis in memory cache to get the counter value to check whether this request can be forwarded or not. If the counter is less than the threshold and if the request can be forwarded, so the request is forwarded to the API server. If the request can't be forwarded, so there are two scenarios which we can request not forwarded. So there are two scenarios. One is like the request is completely being discarded and we send a 429 request or too many request response to the client. Or another thing is these requests are forwarded to a message queue, you can say, to be handled later. So in case suppose the server is overloaded with some tasks and we need to process these requests later, so these are put into a message queue. So this is a high level design of how a rate limiter is implemented in a single server setup. But we also want this rate limiter in a distributed environment. So in a distributed environment, two factors has to be considered always. We have to ensure how we can handle these two factors. One is, so in distributed environment, we need to take care of two conditions. One is race condition. So in a distributed environment, there will be many users and many servers. So in a highly concurrent environment, a race condition is inevitable. So how do we handle this race condition? So how a race condition happens, let's suppose this is a timeline. So one of the user, so original counter value, let's say, is now 4. So this request comes, request 1, let's say, it reads from the Redis, it updates, it's checked that the counter value is 4. Suppose the threshold is 5, 4 is less than 5, it updates counter in the Redis and forwards this request to the API server. So in the meantime, again another request comes. It also performs a read operation. But since till this time the counter has not been updated to 5, so it will also read the counter value to be 4. And it reads the counter value to be 4. Since it checks that 4 is less than 5, so this request can be forwarded and then it updates counter. So here after it updates the counter, so counter value is like 5, and also when it updates the counter here after the request 2, this value is also 5, but this is incorrect. Ideally this should be 6, so counter should be 6. Yes, so this is a typical race condition which might arise in a highly concurrent environment. So to handle this race condition, one obvious solution is logs. But these logs are very slow in operation and they cause a large amount of overhead, thereby causing a high latency. So this is not a favorable solution. So instead of that, what we use is we use Lua scripts, or you can say sorted sets data structure to handle this race condition. So Lua scripts works on atomicity of operations. So it works in a atomicity of operation manner, thereby maintaining atomic operations and thereby handling the risk conditions. And this also, so you can read about this Lua scripts or sorted sets data structure in Redis. I'll post the links in the description. And this, I'll just go in a high level. What is this? So Lua scripts works in a atomic manner, thereby handling the risk condition. And sorted set data structure in Redis is a data structure which basically stores the scores of requests in form of timestamp. So, and this also works, another thing, this is most preferred with sliding window algorithms. So these are the two solutions which is basically implemented in handling risk conditions for distributed environment. So one is the Lua scripts and another is the sorted sets data structure. Locks are not being used because of its high latency. So in this way, risk conditions are handled in a distributed environment. Another is, like we mentioned, so another issue which is need to be handled is the synchronization. So what is the synchronization issue? So to support millions of users, so one rate limit server is not sufficient to support a huge number of user requests. So suppose we have multiple servers, rate limiter servers, server 1 and server 2, and the client 1, client 2, they both send the request to server 1 and server 2 in a case 1 scenario, or say timestamp 1. In timestamp 2, since the web tier is stateless, the client 1 can send the request to server 2. Maybe this is handled by a load balancer where it will send the request, and this is also sent to server 1. But in both the cases, earlier the data for client 1 and client 2 was handled by server 1 and server 2 respectively, but in this scenario, server 2 has no idea about client 1, and same for the case of server 1 for client 2. So thus, to handle this situation, to handle the synchronization of the counter values, we use a centralized data store. So this is a centralized data store called, which we have discussed earlier, this is Redis. So basically we add Redis here, and whenever the request comes to server 1 or server 2 from client 1 or client 2, either one of them, the Redis stores the data for the counter value, the timestamp or the expiration period, and we get a uniform data from this Redis instead of any synchronization issue. So this is one thing which we handle, like synchronization issue and race condition in a distributed environment. Next, one other topic which we will look into this distributed environment is performance optimization. So we require actually a multi-data center setup, right? As we have also discussed in a key value store playlist, you can go through that. We require a multi-data centers setup, since for a large number of users this will cause a latency which for users located away from the data centers. And for that, what we see is we have a large number of edge server provided by the cloud service providers across the globe. Cloud service providers across the globe. And to maintain the consistency between this between the servers in the multi data center setup, we follow eventual consistency. So this about eventual consistency, I have discussed about this in my designer key value stored playlist in inconsistency resolution video. So I'll post a link about it in the description, so you can go through about eventual consistency. So this is nothing in a high level. If I describe what is eventual consistency, so like to maintain the high availability of the data centers, we read the data from the servers. The client actually handles the logic of keeping the latest data and then updates this latest data into all the servers where the data has been replicated. So this is eventually the consistency is being handled. So in this way we optimize our performance. So first we set up a multi data center setup, and the various edge servers are provided by the cloud service providers across the world, so that the users do not have to rely on data centers which are located far away, thereby causing a high latency in the performance. And to maintain the consistency among the multi data centers servers, we follow a method called eventual consistency. Another thing is like after the rate limiting algorithm or the rate limiting rules has been implemented, we also place a monitoring method system. So this monitoring system is being used to check whether this rate limiting algorithm or rate limiting rule is effective or not. So let's say suppose our rule is very strict and it causes a large number of valid requests, thereby causing large number of valid requests to be dropped very frequently. So in this case we can make or relax our rule a little bit so that the large number of requests are not dropped and they are being handled efficiently. Another case for the algorithm, it might be like in case of a flash sale, a large number of requests comes, but our algorithm is not effective to handle this large number of requests. So in this case we can replace our algorithm with let's say token bucket algorithm, so which can handle, as you have also seen in my algorithms video about this rate limiter, token bucket algorithm can handle a large burst of requests in a short span of time. So in this way we monitor our rate limiting algorithm or rate limiting rules to make our environment or distributed environment, make our entire setup to be highly efficient. So in this distributed environment scenario, what we have discussed, just to recap, firstly this is a single server setup which we have discussed about in the previous video. This is a recap of a high level architecture in a single server environment. In a distributed environment we actually face two conditions which we have to take care of. One is the race condition. So race condition is being handled using Lua scripts which works on atomicity of operations, and another is sorted sets data structure in Redis, which I will share the link in the description, you can go through them in details. And another is the synchronization issue, which we handle using a centralized data store like in memory cache called Redis, instead of relying on the servers which can be dynamic for a particular request sent by a client. And to optimize our performance, we have to set up a multi data center setup for a distributed system, and for this cloud service providers provide us with edge servers which are being distributed all over the world, thereby reducing the latency for a particular user to query a request. And we also maintain eventual consistency for the servers located in multi data center setup. Also we monitor the rate limiting algorithms and the rules so that our entire system is very much efficient. For the algorithm, let's say suppose we have a scenario when in case of a flash sale, a large number of requests are being influxed into our server, and our algorithm is not that much efficient to handle those large number of requests, so we need to change the algorithm. In that case, token bucket algorithm works much better. And suppose our rule is very much strict and a large number of valid requests are dropped in a particular period of time, and our server is capable of handling those amount of requests, we can relax the rule. So this is overall all about our rate limiter, what we have discussed in all the videos. So thank you for watching the video. Stay tuned for more videos and see you in the next video.